Welcome to the final video in our System Devices 2 networking series. Again, we're going down that protocol stack to the final layer, layer 1, our physical layer. So some good news, we've finished looking at protocols. There's no more protocols in layer 1. Well, most technically, your Ethernet protocol is in layer 1 and layer 2. But for us, the last thing we're going to be looking at is what actually is pushed out onto the wire, electrically speaking. How is our data encoded in our Ethernet frames? So yeah, we're down into layer 1 now. At this level, our unit of data is bits. So the raw bits that we are squidging out onto that wire. Those electrical signals we're sending down that copper wire, or the pulses of light we're sending down that fiber optic cable. So in our Ethernet standard, we start to define distances. So how long a run can you have of your Ethernet cable? The connectors used at the ends of your cable, all of that is defined in your Ethernet standard documentation. So the cables we use in the lab are Cat5, category 5 cables, so copper cables, twisted pairs, and down those twisted pairs we send our raw bits. And an optional extra for our final labs, it's a rite of passage, everybody has to make their own Ethernet cable. So we have some high quality, cheap and cheerful cable and connectors. Do feel free to cut a reasonable length of cable and try crimping on your connectors to make your own Ethernet cable. So in the previous lecture, we looked at our Ethernet frame and we saw how they use MAC addresses to identify hosts on the local area network, but what actually is sent down those wires? So here we have an example of a switch. We can tell it's a switch because we've got an awful lot of ports. Switches have lots of ports, and plugged into some of those ports are, as you will recognise, some Ethernet cables. But what is inside those Ethernet cables? Well, we know it's copper wire, but how many wires? How are our bits encoded along those wires? What voltages are used? Also, what frequencies do we send on those cables? What are the limitations of our copper wire? If we're sending 10 gigabits per second down our Ethernet cables, does that mean that a bit changes on those wires every 10,000 millionths of a second? Are we transmitting at frequencies of 10 gigahertz? And as you probably guess, no, we're not. If you look at the frequency range for radio frequencies, we'd have a hard time persuading those bits to stay within the wire, because obviously once you get up into the gigahertz kind of region, you're in the land of UHF, ultra high frequency transmissions. So your copper wires will start to act like antennas. So what we typically find is that we need to reduce the frequency components that we use to transmit our data. In general, copper wire does not like high frequencies because you'll find that the natural resistance, inductance and capacitance associated with your cable will start to attenuate those higher frequencies. So frequencies around about 10 megahertz, that's normally kind of okay. And you see that back in the day when we had 10 base 2. We could send our Ethernet data quite happily down 200 meters of coax cable, and you could still receive the data at the other end with some cheap and cheerful hardware without going too exotic and specialized. However, as we want to transmit more bits per second down our cables, obviously the frequency components will increase. Now, if you increase the frequency, those higher frequencies will be attenuated more severely, so your cable runs will have to be shorter. So if you look at your 100 megabit, gigabit and 10 gigabit, you'll typically see that your cable lengths are limited to 100 meters or less. And the higher the bit rate, you have to start to use more exotic cables with increased levels of screening. And equally, the electronics that you'll need to receive that data needs to be more specialized, as the data you put on at one end of the cable at the transmitting end will not look the same as it gets to the receiving end. It will be severely attenuated. However, as long as you can differentiate between the different voltage states, then that's perfectly fine. So yeah, as we go up to higher data rates, our frequency components within the wires do increase, but there is a limit. You can only send signals down a wire so quickly. Because effectively what you have to do is move electrons on and off that wire. And there are limits. So when you are transmitting data at gigabits per second speeds, you'll typically see the frequency components on the wires are limited to, again, a few hundred megahertz. Because that's the physical limits that we can move electrons on and off the wires. So therefore we have to do some clever stuff to allow us to increase our data rates, and we'll have a look at that one in the later slides. But yeah, 250 meg or so is probably what you're looking at topping out at. Unless you're going to really expensive cables, and even then they would be significantly shorter lengths. Alternatively, you can avoid all of these problems associated with resistance, inductance and capacitance by going to fibre. So if you go to fibre optic cables, obviously you're transmitting your data now as pulses of light, so all of those issues are removed, and that's what you tend to see. So if you're going for longer cable runs, kilometers worth of cable, then that'll be fiber. And the additional advantage of that is obviously copper wire will act as an antenna. It will pick up electromagnetic interference, whereas a fiber cable obviously is completely immune to that, which makes it a lot more reliable. Radio then, back to some basics. How do we communicate stuff across our electrical wires? Well, you've got two choices. We can do that in parallel or in series. So we have parallel buses and we have serial buses. Those buses may be synchronous or asynchronous, with or without a clock. So if you look at an example here, these are examples of synchronous serial and parallel buses. So if we took our parallel bus, for example, we have 3 wires, 1 carrying our clock and 2 for our data. So we can transfer 2 data bits on 1 clock cycle. So typically what you will see is that the transmitting host will transmit the data on one edge of our clock. So in this case here, the falling edge, that gives that signal a little bit of time to settle down until it reaches the required voltage level, in this case to represent a logical 1. And then on the following rising edge, that's when the receiving host will clock that data through into its receive buffer. So you can see here it's receiving the value 1, because this is our least significant bit and that's our most significant bit. So in this case here, on this edge, we're capturing the value 0, 0, and then on this one here, we're capturing the value 1, 0, 1, then 2, 1, 0, 0, 0, and then 1, 1 for value 3. So we're transmitting the data values 0, 1, 2, 0, 3, 0 as we're going through there. Just our data values. So you can see there, the more data bits we have, the more data we can transmit, the bigger the value we can transmit. So you'd see that on the data bus of your processor. So typically you'd have a 32-bit or a 64-bit bus allowing you to transfer that many bits per clock cycle. Obviously, the advantage of that is it's fast, it's parallel, but we need a lot of wires. And that's not necessarily what we want when we've got long cabling runs. Perfectly fine on a motherboard or inside your processor, because obviously the buses are very, very short. But if you're transmitting data down long cables, many tens or hundreds of meters, that will need more copper. And so that will be more expense for that cable. So what you'll typically see for your networking is we go to a serial bus. And again, example here, we've got a synchronous serial bus. So again, 2 wires, 1 carrying our synchronizing clock and 1 our data. Now that we've only got 1 data line, we have to send our bits sequentially rather than parallel. So now if we want to send the data value 0, we have to send 2 bits sequentially. So again, on that rising edge, again, we're clocking in to the receiving unit. So our value 0, 0. So we're sending the least significant bit first and then the most significant bit. So here again, the value 1. So least significant bit, most significant bit, as we go through that data stream. So we're transmitting a burst of data serially down that wire. So 0, 0, 1, 0, 0, 1 for 2, 0, 0, 1, 1 for 3, etc. Again, to reduce the amount of wiring we have, we can go to an asynchronous bus. So we can lose this synchronizing clock. Remember, the good thing about having a clock is that we have a signal on the receiving end telling the receiver when it should look at that data. So the receiving end will look at that data every rising edge because it knows that data is stable on that wire. So when it sees a rising edge on that clock, it knows it can read that data value and it will be the right value. It won't be a value that is changing from one state to the other state, because obviously that would be dangerous. That would be a bad idea. You only want to read your data when it reaches a stable, a consistent value. However, to save some wiring, that's what we do on our networks. We go to asynchronous buses. So now the problem becomes, how do I regenerate this clock signal on the receiving end? So the way we do that is with a preamble. So what we do is we send a sequence of 1s and 0s, just alternating 1s and 0s down that wire before we send any data. And from that 56 bits, 7 bytes worth of 1s and 0s, the receiving end can work out what is the transmitting end speed. What clock rate am I sending the data down at? And we can see that in example here. So if this is the preamble being transmitted onto the wire, so that repeating 0101 signal, the receiving end will sample that. To sample it at least twice as fast as the incoming frequency. And that's given by the Nyquist-Shannon sampling theory. So as always, if you want a bit more information on that one, do have a look at this link here. But this is outside the scope of this module. So this is the period of our incoming signal. So this will be obviously twice the clock frequency of the thing sending it, because on each clock edge we'll be changing the state of this data signal. And as it's received the other end, we need to sample that at these sampling points, obviously twice the frequency of the incoming signal. And you can see here, as we sample it here, the signal is 0, so it was 0. But when we sample it here, it's a 1, so we set our internal representation of the signal to 1. Sample here has gone back to 0. So you can see it's not a direct copy of the original signal. Its mark space ratio is not the same, but the frequency is the same. So we can work out what the transmitting frequency is, such that when we look at our serial data coming in, we know when to sample it, and that's the key bit. That's why we're regenerating this clock. So our transmitting end will send down 56 bits worth of square wave. So each transition here is 1 bit's worth of data. And after that amount of time, the receiving end will have synchronized in onto that clock rate, so it will know when to sample the data signal. To signal the end of our preamble, we have an 8-bit chunk, our start-off frame delimiter. And the difference there is that we get a double 1. So again, in the start-off frame delimiter, we've got an 8-bit value, so it's again still alternating 10 10 10 going through. But you can see there we get a double 1 value. And when the receiving end detects that it receives a 1 and a 1 together, not a 1 and a 0, it knows it's come to the end of the preamble. So the next bits will be data bits from our packet, not synchronization stuff. So as always, there's a little bit of error there. We're not going to get an exact synchronization with the transmitting unit, but if the packets are short, then that's fine. We can stay within synchronization, a margin of error, and sample the data at the correct points as the data comes down. However, if we've got a significant amount of data within our packet, then there's a possibility we'll start to lose synchronization. So we'll start to see some drift in our clock. The receiving unit will start to sample the data at the wrong points. So that's not too bad if our data signal is changing. So if you look at this example here, so signal A, so we know that on every transition here, this will be a change in the transmitting unit's clock, because that triggered the change in the data. So on each edge, we can resynchronize the receiving machine's clock so it keeps in step with the transmitting machine. However, you don't always get a nice changing waveform. Sometimes you have big long bursts of zeros or big long bursts of 1. So in this example here, there's only one synchronization point. So if you had a very long string of zeros or a very long string of 1s, again, over time, you'll start to lose synchronization at the receiving end. So we call this way of encoding our data a non-return to zero encoding scheme, as the signal here does not change when your data doesn't change. So one way around that is to change the way we encode our data. So rather than encoding our data via a level, for example, so typically you'd see here like a logical 1 would be represented as a particular voltage level and a logical 0 would be represented with a different voltage level. So let's say, for example, 1 volts for logical 1 and 0 volts for logical 0. So here we're encoding the digital value by the level. An alternative way of doing that is to encode it via a transition. And we call this Manchester encoding, self-clocking encoding. So a logical 0 is encoded from a 0 to 1 transition. So it's not the level now, it's the transition from a 0 to 1 tells the receiving machine that you have transmitted a 1. So now if you have a sequence of 1s, you will have to return to 0 such that you can do that 0 to 1 transition for the next one. If you are transmitting a 0, then you'd have the opposite. You'd have a 1 to 0 transition. So again, if you have a string of zeros, you have to return the signal back to a 1 so that you can have a transition from 1 to 0 to transmit the next 0 there. So the way to think of it is a rising edge encodes a 1 and a falling edge encodes a 0. Now we have a signal on the wire that is changing more frequently. If you compare this one here with this one here, there's more clock edges, so there's more chances for the receiving end to resynchronize its internal clock to the transmitting clock, so they stay synchronized, they stay in lockstep. And we call that phase encoding rather than level encoding. So that's very nice from a clock regeneration point of view, but from a frequency component point of view, as you increase the frequency to achieve higher data rates, we start to see significant higher frequencies. And as we discussed previously, there's a limit on how fast you can send data down that wire. There's a limit to what the maximum frequency is for a particular cable. So we want an encoding scheme that allows us to resynchronize our clock on the receiving end, but we want that encoding scheme not to increase the clock frequency too much. So you've got competing demands on your encoding scheme. And if we dive too deeply into the electronics, you also have a problem with DC bias. So our cable will have resistance, capacitance and inductance associated with it. And effectively what that means is that you can charge up the voltage on that cable. So you can see here, this is what the signal may look like on the transmitting end. But you can imagine those voltage pulses that we're driving onto the wire will charge up that capacitance in that wire. So what that will mean is that at the other end of that cable, you don't discharge the voltage on the cable back down to zero. There'll be some standing voltage on that cable. So now our noise threshold isn't from 0 volts to 1 volts. It's somewhere in the middle. It'll have some DC offset, which makes it more difficult for the electronics to detect whether you're receiving a logical 0 or a logical 1. In addition to that, we need to consider electrical isolation. Obviously, there's a danger if you connect a cable to any computer that rogue signal transients, pulses of voltage can enter the computer along those cables. So if there's a big electromagnetic discharge near those cables, a lightning strike on the building or something, then there's a real danger that those cables will pick up that voltage. A voltage will be induced into that cable, and you do not want those cables directly connected to the electronics in your computer, as obviously that will cause every computer on that network to blow up. So therefore we want to isolate the electrical signals used to transfer our data on the network from the electrical signals in our computer. And to do that we typically use a transformer. And if you have a DC bias on your cable, that means you're saturating your core of your transformer, which I know means that I'm going into too much detail for those who haven't done electronics, but just take it from me that this is bad. Basically, it means you make it more difficult to receive the signal at the other end. So if you have an encoding scheme that just uses 0 volts and a positive voltage to encode the various states, then this problem can occur. We call this a unipolar encoding scheme. So the way around that one is to go to bipolar. And that's what we see in our next encoding scheme, in multi-level transmit encoding or MLT encoding. In this particular case, we're using MLT3. So there's 3 voltage states used to represent our logical ones, which are a positive voltage, a 0 voltage, and a negative voltage. So the easiest way to think about this one is, imagine you've got a sequence of ones. So now to transmit the logical 1, we're not using a level to represent the 1 state, we're using a transition within this sequence of voltages to encode the logical 1 state. So for example, the first one will be represented by a minus voltage. Then if you want to transmit the next one, that will be a transition from the minus voltage to 0 volts. If we want to transmit another one, that will be a transition from 0 volts to positive voltage. If you want to transmit another one, that will be a transition from a positive voltage to 0. And again, if you want to transmit another logical one, that will be represented by the transition from the 0 volts back to the minus volts. So you can see, if you are transmitting a long block of logical ones, then the average voltage on the cable will be 0, because you will have one of your ones represented by a minus voltage, which will be cancelled out by a following one represented by a positive voltage. So the two voltages will cancel each other out, so the average DC bias on the cable will be 0. Now to represent our logical 0, we just maintain the current voltage level. And you can see that in this diagram here. So if we're starting off with a 0 voltage, we're in this 0 volt state here. You can see to transmit a logical 1, we transition to the positive voltage state. To transmit our next one, we will transition to 0. So we go from positive to 0. Then if we are transmitting zeros, we stay in the state that we are. And at the moment we're 0, so it'll stay in the 0 state. So no change represents a 0. Then we want to transmit another 1, so we will move from the 0 state to the minus voltage state. Next we want to transmit a 0, so again we do not change the state, so no change of state is a 0. Now we want to transmit a 1, so we transition from a minus to a 0. And now we want to transmit another 1, so from a 0 to a positive. So you can see by doing this that the average voltage on the cable will be 0, because the positive voltage and the negative voltage on average will cancel each other out. However, in our effort to remove DC bias, we have reintroduced our synchronization problem, because if you were to transmit a long block of zeros, your signal does not change again. So our receiver could become unsynchronized because it can't regenerate the clock. It needs transitions in the data stream to regenerate that clock. So we have to combine MLT with one final stage of encoding. 4B5B encoding. So rather than transmitting the actual data values, we break those data values up into 4-bit chunks and transmit a 5-bit representation. And that 5-bit representation has been chosen such that the worst case continuous string of zeros is limited to 3 zeros in a row. Obviously, we don't care about ones, as that will generate a changing signal on the wire. It's only the strings of zeros that we're trying to replace here. So if we look at this in more detail, we can see that a 4-bit data value of all zeros would be transmitted on the wire as 4 ones and a 0. So again, that'll be a nice alternating signal. Then our next 4 bits, if we had 001, that will be transmitted by this 5-bit code. So again, the transmitting process will be to break down your data into 4-bit chunks and then replace those by this sequence of bits on the wire. The receiving end will receive those and do the opposite translation. It'll take that 5-bit value and convert it back into a 4-bit code, which is actually your required data. So we've solved the problem, and if you were to look at the raw bits being transmitted between your Raspberry Pis in your base systems, that's what you'll see on the wire. So we use the MLT3 representation on the wire as our voltage levels, combined with 4B5B encoding. And the two together remove all the problems we had previously. So we remove the DC bias problem and we remove the long strings of zeros so we can resynchronize the clock at the receiving end. Okay then, so we've looked at some different ways of encoding our data. So we saw in 10BASE-T, we could use simple unipolar Manchester encoding to transmit our bits. However, if we want to go faster and we went to 100BASE-T, we need to send our data obviously 10 times faster, and that starts to add some problems. We get a DC bias in the cable, and we need to make sure that the receiver can stay synchronized with the transmitter. So we move to MLT and 4B5B. As you can probably guess, if we go to 1000BASE-T, we get even more problems because again, it's 10 times faster. And yeah, you don't want to look at that one. It gets significantly more complicated to transmit data down copper wire at that speed. However, you can see there are a number of different Ethernet standards. Some use copper and some use fiber optic cables. So one thing that allows them to work at different speeds are the number of channels used, so the number of pairs of twisted wires used to communicate the data, but also the types of cables. And these are identified by their CAT number, the category number, as you can see listed here. So the ones you'll typically see in the lab are category 5 or Cat5 cables. And as you can probably guess, a cable designed to carry 10 megabits per second will be a lot cheaper to make than one designed to carry 40 gigabits per second. So that's what we'll look at next. We'll have a look at our different types of cables. So these cables will fall under the categories of UTP, FTP, STP, SFTP, UFTP, FFTP. SFTP and SFFTP. Can you name them all? But basically, we've got ever increasing amounts of shielding to protect our signals, to stop crosstalk, to stop our signals being corrupted by external electromagnetic interference. So to see what they actually look like, we can have a quick pop to this webpage. So a normal Cat5 cable is a UTP cable. It's unshielded twisted pairs. So you've just got 4 twisted pairs of cables that your data sent along. So there's no shielding between the various cables and there's no shielding from outside noise sources. The next step up in performance is to add some shielding to those 4 twisted pairs. So you can either add a layer of foil around all the cables to shield them from external interference, or some copper braid, or both. And that will obviously screen out, give you your Faraday's cage effect to shield out any noise. Next, what we can do is to stop crosstalk between the various communication channels by shielding each twisted pair. And you can see that here. So here, each twisted pair is wrapped in its own foil shield. And then, as we did previously, we can add a copper shield for the whole cable, or braid, or both. So basically, we're adding increased levels of shielding to the cable and the individual channels within that cable. And that will help improve your signal to noise ratio, which will hopefully reduce the number of packets, the number of bits that are corrupted by these noise sources. What you also see when you go from Cat5 to Cat6 is you see an internal former. Basically an X-shaped piece of plastic designed to keep the 4 twisted pairs separated so that they don't wrap around each other or increase their inductive and capacitive coupling. And you'll see that in the lab. So if you look at the grey cables connecting the USB to Ethernet adapters to the switch and compare their flexibility to the red, yellow and blue cables connecting the Pis to the router, you'll see those grey cables are a lot more rigid, as they are Cat6 cables with this internal plastic former, whereas the red, yellow and blue cable are Cat5 cables and they don't have this internal former, so they're a lot more flexible. And that's something to remember if you're trying to run some wiring. Cat6 cable is a little bit more stubborn to go round corners. To allow us to connect our twisted pair cables to our routers and our switches and our hosts, we need connectors, and those connectors are called RJ45 connectors. These connectors have 8 pins because you've got 4 pairs of twisted wires to connect to your various devices. And to allow you to experience the sheer joy of crimping these connectors onto cables, you can do that in this week's lab. So you have a reel of cheap and cheerful Cat5 cable and some connectors. So yeah, do make your own Ethernet cable. As I always say, it's a rite of passage for any network engineer, and it can be a bit fiddly, especially if you're optically challenged like myself. So there's 2 flavours of cables, straight through and crossover. Typically today you'll just see straight through cables as illustrated here. So you can see our 4 twisted pairs are identified by colour. So you've got the brown, orange, blue and green wires. And those are your 4 twisted pairs. And on gigabit connections, you can use that cable to connect switches to switches, hosts to switches, hosts to routers. It makes no difference. But for the older standards, it does. So if you've got 10 base T or 100 base T, then you may need a crossover cable in certain scenarios. So in these older standards, the pins that transmitted data and received data were fixed. They were hardwired to certain pins. Nowadays, with gigabit links, it will auto detect and determine which pins should be transmit and which will be receive. But in the older standards, such as 100 base T, your host, your PC, would transmit on 1 and 2 and receive on 3 and 6. So on your switch, it would therefore have to receive on 1 and 2 and transmit on 3 and 6. The other way around. So in the connector, it was constructed that way. So if you wanted to connect a switch to a switch or a PC to a PC, that wouldn't work, because obviously if these both ends were plugged into PCs, one PC will be transmitting on these wires and the other PC will be transmitting on these wires. So the transmitted data would never get to the received pins on the other end. So that's why you had a crossover cable. So you can see this one here, you can see if one PC was transmitting on 1 and 2, those would go to 3 and 6 on the other end, which were the receive pins for that PC, and this PC would transmit on 1 and 2, and his data would go to the receive pins on the other end. So that works perfectly fine. So for those older standards, yes, you sometimes need crossover cables. But nowadays, because we use gigabit links that can auto-detect which pins are transmitting and therefore which pins it should receive upon, we don't need those anymore. Everything is straight through normally. So when you're constructing your cables in the lab, I'd go for a straight through cable. Keeps things nice and simple. So yeah, as I was saying, for the older standards, you may need a crossover cable in certain scenarios, but with the move to 1000 base T, it will detect those using the link integrity tests. Basically another low-level protocol running across that cable. In addition to that one, whereas the older protocols hardwired pins as being either transmit and receive, in 1000 base T, now all pins are bidirectional, allowing them to be transmits or receives as needed. Also, when you plug in your cables, obviously, you may be plugging in new hardware with old hardware. So your PC may be able to work at 1000 base T gigabit speeds, but you may be plugging your cable into an old hub, which is only supporting 10 base T. So you need a way for each host to identify what standard it should use. Because typically, if you can do gigabit, you're backwards compatible to earlier standards. And the way they do that is by using your normal link pulse. So back in the day of 10 base T, to detect link integrity, when data wasn't being transmitted, your host would send a single pulse onto the wire to say, I'm alive. So every, I think, around about 16-ish milliseconds, it would send a 100 nanosecond pulse to the receiving end just to confirm it was still there. Over time, that capability has been turned into the auto-negotiation part of the 802.3 standard. So using these normal link pulses, we can send a sequence of these pulses down the cable when we first plug in to tell each end what standards we do support, so that we can agree upon what standard to use. And what we will see in 2 ticks is that even when you're not transmitting stuff nowadays, the line is always busy because it's got this link integrity test going on all the time. Okay then, so for the final part of this lecture, we're going to actually look at some of the voltages on these wires. So what I've done is cut open a Cat5 cable so you can see our 4 twisted pairs there. Kind of just about see that they all do have slightly different twist rates, which I believe helps answer some of these questions down the bottom here. So the first one is, okay, we saw with other cables that they had multiple layers of shielding. Why can we get away with not having any shielding in Cat5? So how does Cat5 cable get rid of noise? And yes, we've looked conceptually at how our data is represented on the wire, MLT, 4B, 5B, Manchester encoding, but what actual voltages are used on the cables? So by peeling back some of this insulation on these cables, I can connect a scope to those wires and we can see what actually is going on the actual cable. So proper layer 1 stuff. So on each twisted pair we send the data and an inverse of the data. So you can see here when it goes high on one wire of a twisted pair, it will go negative on the opposite wire within the twisted pair. And what we're trying to do here is cancel out the magnetic fields, or forgive me, Fleming's left-hand rule, but if you've got current going down a cable, it will generate a magnetic field in a direction. So if you put the opposite voltage on the wire, the current will flow in the opposite direction, so you'll get an opposite magnetic field, and fingers crossed, touch wood, those twisted wires, their magnetic fields will cancel each other out, so they do not induce voltages on the other channels, on the other twisted pairs within your cable. So having differential signaling, sending the positive and the inverse down those twisted pairs, we can hopefully remove or at least reduce that part of the interference. So we can remove the noise generated internally in the cable due to inductive coupling between the wires, because we're cancelling out those magnetic fields. That doesn't help with capacitive coupling, so just the cables being physically adjacent to each other. So one way of reducing that one is to go with Cat6. Obviously you have that plastic spacer so you can move the cables away from each other. That would help. And also what we can do is take advantage of this differential signaling. So if we have the same signal on 2 wires but are inverted, if we subtract those signals from each other, then any common mode noise, so any signals that were picked up equally on both wires, will be removed, because that will have the same amplitude on both wires. So when you subtract those signals on those wires from each other, that noise will be removed because it's common to both wires. However, the actual data signal is the inverse. So you get the minus minus. So you reinforce your signal and remove your noise. So you'll get a better signal to noise ratio. And that's what I'm showing here. So these are the traces captured on the scope. So you can see as our data bit goes high on one wire, it goes low on the other wire. So we get positive voltage minus a minus voltage, which doubles our signal, gives us a nice larger signal, which helps us when we're thresholding, is it a 0 or is it a 1? Because it separates the logical levels. So they're less susceptible to small noise variations, which will occur in any digital system. So yes, this is perfectly acceptable in terms of digital signals. You do not get nice square waves when you actually look in the real world. You only see square waves when you look at textbooks. In the real world, everything is noisy. Everything wants to revert back to that sine wave. Okay, so I'm going to record this one ahead of time, as doing this demo live in a lecture review session is guaranteed to fail because there's so many things that can go wrong. It's surprising how noisy a lecture theatre is, electrically speaking, which means setting up your scope, triggering a scope becomes even more problematic. So recording it in advance is what I'm going to do. So here we have our pin functions. So we've got pins 1 to 8. So for 100 base T, you can see certain pins are TX and others are RX. 1000 base T, as I said, everything is bidirectional now, but we still have to be backwards compatible with the older standards because you may have a new device connecting to an older device. So again, you can see I've got a twisted pair on pins 1 and 2, and the B twisted pair again is on 3 and 6 because that's what the older standards define. But 1000 base T, you've got 4 bidirectional channels. So we will have a look at our 100 base T signal. So that's the MLT3 with 4B, 5B encoding. But on a scope that is particularly hard to read, so you probably already spotted what I'm going to do and cheat. So this here is Manchester encoding. So what I'm going to do to make my life a lot easier is I'm going to connect the Raspberry Pis, not through the switch that we use in the lab, which would use 100 base T. I'm going to connect it through an old hub. So this is an old 10 base T hub, which will cause the Pi to negotiate down to this older standard, so the 10 base T standard. So 10 megahertz using Manchester encoding that we saw in a previous slide, which is a lot more easy to read when you're looking at it on a scope. So that's what I'll do now. And what we're looking at is just some ping packets. So in this example here, we have Pi 3 pinging the router. So we can see ending 13 is Pi 3, ending 14 is the IP address of one of the router's ports. And fingers crossed it should all work. So this is our basic setup. We've got our breakout cable coming through. So these are the 2 points I can connect the scope probes to. If we zoom in a little bit, you can see I'm connecting the scope probes to the orange cable. So this is the orange twisted pair. I'm sure at this point the electronic engineers out there are shouting, what about your grounds? Your grounds, you fool! You're connecting your scope probes to an isolated voltage. There's no common ground. And yes, you're right. But I was trying to show here, by connecting the scope up this way, the advantage of a differential pair. How we can remove that common mode noise. So yeah, I know it's a bodge. The grounds for these scope probes were connected to the shield ground of the USB connector. But we're going to ignore that. With nothing connected, you can see the background noise I'm picking up on those 2 scope probes, and you can see that the purple line in the middle there is the subtraction of these signals, so this signal minus that signal. And as that noise is common to both signals, you can see here picking up a bit of noise on the top trace and the same on the bottom one. When I do the subtraction to produce the purple trace in the middle, you can see that noise is removed, a lot more stable than the yellow or the green trace. Okay, so if I connect Pi 3, so I'm connecting Pi 3 directly to the MikroTik router, we can see our MLT3, 4B, 5B encoded signals, which are quite difficult to understand. And at the moment, I'm not even sending any data. I'm not sending the ping packet. This is just the line integrity stuff going on in the background. As I say, the lines are never quiet. So if I pause this one and we look at the actual signals, we can see what's going on the signal. And yeah, so going from that to raw bits, bit tricky. So that's why I go through the 10 base T hub. It converts this into Manchester encoding, which is a lot easier to understand. So what I do is I'll disconnect Pi 3 from the router and I'll plug that one into the 10 base T hub. And I'll get a patch cable and link it back to the router. So now Pi 3 is going to the hub, and from the hub it goes to the router, so it will negotiate down to the 10 base T standard. So it's a lot simpler to understand. Then when I plug in Pi 3, you can see our signals starting to come through here. Again, a little bit noisy, but if we zoom out a bit, we can see there is our packet of data. A bit of aliasing on the signal there because we're zoomed out quite a lot. So that's why it's all kind of jumping around a bit. But that is our ping packet data coming in. Again, we can zoom in a little bit and we can start to try and analyze what this series of squiggles is actually transmitting. What data do these signals represent? Remembering that a 0 to a 1 rising edge indicates a logical 1 and a 1 to a 0 indicates a logical 0. Other key things to note here is that obviously this is a 10 base T system, so we're running at 10 megahertz. We're at 100 nanoseconds per division, so these grid points are your sampling points. So this is when the data is stable. You can ignore the squiggles in the middle, so that is the key point. So the receiving end will be looking at the signal's voltage level at these sample points every 100 nanoseconds. So here you can see it's gone from a 1 to a 0, so that encodes a logical 0. And from here it goes from a 0 to 1, so that encodes a logical 1. So here we've got an example of how you transmit 2 zeros. Remember, there's a sample point here, so that's a 0. So it has to go up so that can come back down again to transmit the second 0. Every sample point here. So again, this is a 0 to 1, so that is a 1 being transmitted at that point there. So to transmit another 1, it has to go back down again so that it can go up for the next sample point at the next point in the signal. Okay, a nice feature of these digital storage scopes is that we can take a screenshot. So you can dump what's been displayed on the screen and save it off as a bitmap, as an image. And that's what I've done here. what we have is a freeze frame of the start of the communications session. So a point in time before we start to send those ping packets. So on the far left of our screen, we have the default state of our differential signal pair. So at the top one, we have our TX plus, and the bottom one, we have our TX minus. And the purple trace in the middle there is the combination of the two. So the purple trace is a maths function on the scope. And what we're doing is we're subtracting the green bottom trace from the top yellow trace, and the subtraction of the two produces the purple trace in the middle. So to start off with, there's nothing being transmitted on our wires. That's a good advantage of 10 base T. And then we start to send our preamble, so our sequence of ones and zeros. So you can see if you look at the purple trace in the middle, we have a rising transition on the sample point. So we're going from the negative voltage state to a positive voltage state, so that encodes a logical 1. And then at the next sample point, we've got a transition from a positive voltage to the negative voltage, so that encodes a logical 0. And we repeat that pattern because that is our preamble. Our preamble is a 56-bit sequence of ones and zeros. So every 100 nanoseconds, we'll be transmitting a new bit of information. To signal to the receiving host that we are now going to send the actual data, we need some sort of flag in the preamble to indicate when it has finished, and we do that with the start frame delimiter. And what that is rather than going 1010, we end with a double 1, and that double 1 indicates to the receiving host data is to follow. So what we have here in this screenshot is our first actual data packet. So this bit here is the end of our start frame delimiter, our double 1, and then the bits after that are our first byte. And the first byte of our Ethernet frame will be the destination MAC address. Bits are transmitted least significant bit first, and so you can see by going through and analysing the rising and falling edges, we have received this data value. So remember that one for the moment. Okay then, this is a screenshot of the second byte of our destination MAC address. And on the left hand side, we have the last bit of the previous byte indicated. So if we analyse the rising and falling edges again of the next 8 bits, we will see that we have received this data value. So again, write that one down. Don't worry, this is the final byte we'll be analysing in our destination MAC address. Again, on the left-hand side, we have the last bit of our previous byte. So the bits following that will be our 8 bits associated with our third byte. If we analyse those rising and fall edges, you should see that we get this data value. Again, note that one down. So to see if our analysis of those squiggles was correct, have we converted that Manchester code into the correct ones and zeros, we need to know what we were actually sending onto the wire. And if you look back at the previous slides, you'll see that we were sending ping packets. So we're putting our Ethernet frames onto the wire, so we'll send the preamble, then the start frame delimiter, and then we'll have our Ethernet frame header, and they will contain the destination and source addresses. So in Wireshark, if you highlight the Ethernet packet part of our capture, we can then see what that header will be and what data it contains. So the first element of our Ethernet header is going to be our destination MAC address. So if you look at that one, we'll see the values 48, 8F, 5A, CF, D5, 8A. And if you look back at our 3 bytes that we analysed, you'll see that those first 3 do match. So 48, 8F, 5A are the first 3 2-digit hexadecimal values in our 48-bit MAC address, our 48-bit destination MAC address. So fingers crossed, touch wood, after that ordeal, you can now see the matrix. You'll look at those squiggles on the screen and you will see ones and zeros. So one final quick quiz. Knowing what you know about 10 base T, 100 base T and 1000 base T, gigabit communications, if you look at this switch and you look at what pins are available in the various ports, can you identify what standard it doesn't support? So if you think about this table here and the various pins that are used in 100 base T and 1000 base T, can you see that something is missing? One of those protocols will not work. And I guess it makes sense. You can save a little bit of money by not putting in something that is missing from those connectors. Rightio then, this is the last slide. So we have now finished our journey through our protocol stack. So fingers crossed, touch wood. You've got a good understanding of how a network works, from the application layer all the way down to the physical layer. If you would like to take your networking knowledge further, as I suggested in the first lecture, do have a look at the Cisco online exams. So you can do your Cisco technician level training for free on the Cisco webpage. work through their course material. And if you want to take it further, do consider your CCNA exams. Definitely a recognised qualification if you're interested in moving into the network sphere. Okay then, so that's it. No more lectures. I will not see you next time.